Example 11, we want to write the contrapositive of this following theorem. If the sum of a sub n, so there is our infinite series, if it converges, then the limit as n approaches infinity of our individual terms approach zero. So this is, I made reference to this particular fact at the very beginning of the lesson, that if we have a convergent series, then all of the terms have to be approaching zero. Like the individual terms, they have to be getting smaller and smaller. I must be adding tinier and tinier things to my sum, right? So this as a particular theorem is not terribly helpful because it doesn't give me any particular thing to be able to test for. The contrapositive, on the other hand, it just might. So if you have forgotten, let me give you a little bit of a kind of geometry background here, that an if-then statement is usually written like this. P implies Q. And then it's contrapositive. You flip it and you negate it. It's not Q implies not P. And we care about contrapositives because if the original one is true, then the contrapositive is automatically true. They're called logically equivalents. They have the same truth value. So the contrapositive in this case is going to be a lot more useful. So this one is the if statement is our P here, our then statement is our Q. We have to flip them and we have to negate them. So the Q part, the limit part has to come first and I have to negate it. So it's going to say if the limit as n approaches infinity of our individual terms is not zero, then the sum a sub n does not converge. If it does not converge, that means it diverges. Now, when we state our theorem like this, it's a lot more helpful because it gives us an initial test to check. It's like, oh, well, if these terms, the individual terms, are not getting close to zero, I'm done. That thing is never going to converge. But another thing to note is just because the limit of the terms approaches zero does not necessarily imply that the thing converges. I don't get that from this because it all comes down to, okay, so maybe they converge, but do they get there fast enough? If you remember whenever we did our improper integrals, that we had some examples of these improper integrals, this area that's going close to shooting off to infinity, but sometimes it converged to a particular number and sometimes it went to infinity. And it was all about how fast it collapsed down to the x-axis. And this is very similar to that. All right, so this leads us to something that we're calling the nth term divergence test. Please make note. If the limit as n approaches infinity of the individual terms of your sequence, a sub n, if that's not zero, then our summation, our series is going to diverge. Okay, so again, in other words, if the individual terms of your sequence are not approaching zero, this thing is not going to converge, it's going to shoot off to infinity. And then, as I said at the beginning of this, is that just because the limit is equal to zero of your individual terms, you know nothing, right? So as a first check, it's always a very easy thing to check right up front. Take the limit of your little sequence, the individual terms of your sequence. Is it equal to zero? Okay, then you can keep going. You must check something out. But if it's not zero, you're completely done by the nth term divergence test. Okay, so just think about this. Let's say that the individual terms are approaching the number 2. Then that means that individually each term is trying to take on the value of 2, and I'm adding up an infinite number of 2's. Well, obviously then that thing is going to shoot off to infinity. But if our individual terms are getting closer and closer to 0, then it's like I'm trying to infinitely add up a whole bunch of zeros, and then that could converge, but sometimes it doesn't. So let's apply that to example 12 here and determine whether each of these series converges or diverges. I've got on the very first one 2 to the n. Sum 2 to the n. Well, this one's geometric. I could use the geometric series test on this one because our common ratio is 2. 2 oops, here, let me make that as an r is equal to 2, definitely bigger than 1, so therefore this thing diverges. Great, so that's linking that back to our geometric series discussion that we had in a previous video. But if I were to take the limit as n approaches infinity of just this individual term, which is 2 to the nth right there, obviously that's going to shoot off to infinity. And so I can also say that it diverges by this nth term test for divergence. Okay, so let's look at number 2. Number 2 has some factorials in it. Ooh. All right, so I've got, I want to take the limit of each one of these. I want to take the limit. This is definitely not a geometric one, so I can't use the same kind of technique that I did before. N goes to infinity. N factorial over 2n factorial plus 1. Okay, so now on this one, we can take kind of a pre-cal kind of rule. It's very similar to having something like 2 to the n over, not 2 to the n, 2 times n over 2n plus 1, right? You still get an infinity over infinity. And now factorials are not something that you want to take the derivative of. So instead, I want to use that kind of pre-cal notion where I'm going to take the ratio of the leading coefficients here. This limit is going to approach a half. All right, since that approaches a half is definitely not 0. In other words, each one of the terms of this sequence are getting closer and closer to a half. We're adding up an infinite number of 1/2s, which means that this thing is going to absolutely diverge. It diverges by the nth term test for divergence. All right, last one. I've got the summation probably from n equals 1, not n equals 0, to infinity of 1 over n. All right, so I'm going to start it just like I did number 2 here. I'm going to take the limit. N goes to infinity. 1 over n. 1 over infinity. That's going to definitely approach 0. We're in good shape, right? Yeah, we're in good shape, but it doesn't help me with this particular divergence test, because if it's equal to 0, if the limit of the terms approaches 0, there's no conclusion. It could converge or it could diverge. As a matter of fact, this one's a super special series, and we're going to study it in the next lesson. This one's called the harmonic series. Harmonic series, a very, very famous, popular series, commonly on the AP exam. And that's what a whole next lesson is going to be about, that plus some other things, and determining whether or not that series converges, because the nth term test for divergence tells us absolutely nothing. Okay, so let's conclude this video by looking at some properties of infinite series. So we're going to say we have a couple of different infinite series. The first one is going to sum to some finite value a. The second one is going to sum to some finite number b. And we're going to say c is like our scalar, some sort of real number. And then we're going to make some new series based on this. So if we take a constant, the c, times our individual terms in our first series here, well, then that means that our series is going to equal c times a. So it's just that I would have a common factor of c in each one of my terms. I could factor it out. Your series still converges to a, and then we just multiply it by that common factor of c that we factored out, right? Okay. All right, then I can take the sum of two series, and it would just be equal to the sum of each individual series. Of course, this is only true if each individual one is finite and each one converges. We sort of did that with that telescoping one, those two individual pieces that were there. And then the last one that we have here is subtraction. So we can do the same thing. Actually, the telescoping one was more like this one, that we can subtract them, assuming that they both are convergent. Now notice, please, if you will, there's no products and there's no quotients for these properties of infinite series, because you just don't know. Whenever you start multiplying, even though these two things are finite, when you start multiplying them together, dividing them, some strange things can possibly happen. But we can add and subtract them, and we can multiply them by a constant number, and they will still converge. Okay, so let's apply that to this example 13. Find the sum of the series n equals 1 to infinity of 3 over n plus 1, n times n plus 1 plus 1 over 2 to the nth. And it looks to me as if this is a combination of a couple of them that we saw on previous examples. And a matter of fact, it totally is. Okay, so I'm going to rewrite this sum as, I'll rewrite it down first, n plus 1 over 2 to the nth. I'm going to rewrite this like this. I'm going to rewrite this as two individual sums, first of all, 3 over n times n plus 1 plus the sum 1 over 2 to the n. All right. And the one that's on the left-hand side, it has this constant value of 3 in it. So I can pull this 3 out, and I have the sum of 1 over n times, n plus 1. And maybe you recognize that from a previous example. Plus, and I'll rewrite this one as well, is 1/2 to the nth power using a property of exponents. Okay. All right. So what I'm going to use now is the answers to a previous exercise. We already did this one here. This one, if you recall, is equal to 1. So this is 3 times 1. The one on the right-hand side, the sum of 1/2 to the nth power, that's a geometric series. And now recognize, of course, that this starts at n equals 1, not n equals 0. So we need to plug in 1 so we can figure out what our first term is. Why do I have an equal sign there? It should be a plus sign. So our first term when we plug in 1 is going to be 1/2 over 1 minus the common ratio, which is 1/2. And since the common ratio is 1/2, it's smaller than 1, it definitely converges. Right? So I get 3 plus 1/2 over 1/2. 3 plus 1, pretty sure that's 4. Okay. Almost there. Suppose that we have the series from n equals 100 as a starting place to infinity. Okay, let's say that that's convergent. Well, what do we know then about the series that starts at 1 instead? What does it do? What do you think? Well, here's the thing. The idea to take away from this is that if your series converges, if you add a finite number of terms to it, it's also going to converge. So really, we're just missing, the only difference between these two series is like 99 terms. Those 99 things, there's no way that those 99 things are going to add up to something approaching infinity. It might be super large, but it's still some finite number. So this is the main thing to take away from this. A finite number of terms does not affect the convergence or divergence of any series. So if that first one converges starting at 100, if I add an extra 99 terms to it, or 100 terms, or 1,000 terms, it doesn't matter. It's still going to converge. Okay. So that concludes this lesson on series, kind of an overview of series, and in particular, we had things like geometric series. Geometric series are very easy to work with, so if something boils down to a geometric series, I want to look at a common ratio. If that common ratio is less than 1, greater than -1, but less than -1, then it's going to converge specifically to a sum of the first term over 1 minus the common ratio. And then in the coming lessons, we're going to have some different kind of series to be able to have some more tests. We have things like integral, we got p-series, we got alternating series, all of those things to be continued.